All right, everyone. We'll get started with this very exciting April 2026 edition of BrainX Community Live. We have a very exciting presentation coming up, uh, presented by the winners, the first prize winners of the European Society of Intensive Care Medicine Datathon that was held earlier this year. But before that, I see quite a few new faces, and I just want to talk briefly about BrainX Community. So we started BrainX Community close to 7 years ago with the idea that we needed a platform to unite for AI and healthcare for good. And that time we were doing in-person meetings. This was way before COVID pandemic, and we shifted to Zoom because of the need to do it virtually and have global audience. We have a very active LinkedIn group. We have 7,000 plus members worldwide with a lot of diverse background, some from healthcare, clinicians, ML researchers, AI engineers, a lot of diverse background. So we have a very diverse community. We have our website, which I'll showcase. It's a repository of a lot of information and content for AI and healthcare, everything for free. And then we do these monthly webinars where we can learn from each other and we can grow together and share each other's experiences. Either it's for research or for development purpose. So again, here is a snapshot of the homepage. A lot of different content and the latest things right there. This is the connect section. This is where we provide information related to our upcoming events. Also provides links to the YouTube recordings from the prior events. So if you miss it, you can always go back and see over there. Subscribe our YouTube channel so that next time, if you miss an event, you will get the video recording directly to your inbox. As I said, we have a very active LinkedIn group. People share a lot of information over there, content over there, scholarly activities, upcoming conferences, opportunities. So join our LinkedIn group with the name of BrainX Community and be a part of that. We have created our Learn section, which has links to curated publications. There is an infodemic for AI and healthcare, a lot of publications. You want key publications at your fingertips. So the ones that we find are very interesting, have gotten a lot of attention, make it to this page. And here you can even find it filtered by the healthcare specialty of a choice, or large language models or other topics. We also have a data section. In this data section, we provide the largest repository of links to open source data sets. So if you're trying to do your research work, development work, and you need open source data sets, this is the largest repository in the world for links to open source data sets. Of course, we cannot provide the data sets directly. This also you can filter by the healthcare specialty of your choice so that you can find the data set that might be relevant to your work and pertinent to you. We have our podcast that we're going to resume soon, which provides the latest expertise and highlights some of the experts who are working in this space, their journey, their shared experiences, and what they're looking forward to. So you can listen to the podcast on your favorite channel. There is a meetings and conferences section where you can learn about the upcoming meetings. You might want to present your work over there or maybe connect with others who are in the same space. So look out for that. Couple of books that we publish, including one, this is The Voices of Innovation AI, which has voices from or chapter contributions from many of the BrainX community members and their exciting work and their vision for the future. But as I said previously, the really exciting part is the event today, the presentation today. AI agents are being heavily researched, not just in the general world, but also for application in healthcare. We have a very exciting team who is going to talk about their award-winning work and present, what the work that they did. Uh, so I'm going to invite them shortly. Uh, this is the group of presenters and more who will be presenting on this topic. Uh, this recording will be available to you through our YouTube channel too, so you can watch it later on. But with that, I'm going to welcome Dr. Anirban Bhattacharya. I'm going to stop sharing my screen. Anirban, I'm going to give it to you to take it from here.
Thank you, Piyush, for the invitation. Extremely happy to come and present our work here. Uh, so, I will, you know, pass on, the baton to our, teammates who have done a lot of the work on this. But briefly, I'll introduce the concept saying that, you know, it's always been intriguing how we manage ventilators in a heterogeneous patient population. And one of the concerns that we have always had is, one shoe size does not fit all. So, how can we do it accurately? And, given the current tools that we have in today's day and age, we try to approach it, through a multi, algorithm, multi-agent methodology, tying everything together with an orchestrator. Basically, we try to classify, some of our agents would classify the patient as to what kind of a patient they are. The other agent would tell us, what kind, where in the disease process they are, and then each of the action agents would, specifically give an action, and the orchestrator will tie it all together. With that, I would love to invite, Preethi to talk more about it in detail. Thank you.
Hello, everyone. Thank you for inviting us to share our work. So let me just start by just sharing our presentation. Just give me a second. Can you see my screen?
Yes.
So as Anirban pointed out, our goal was to develop a hierarchical multi-agentic AI system for personalized mechanical ventilation. He briefly talked about the clinical problem. And for dealing with this clinical problem, we use the Amsterdam DB dataset. And these are some of the quick metrics that we actually looked at for using this dataset. So we had like around 65,000 patients, and like 62% of them required invasive mechanical ventilation. We had like a lot of ventilation episodes to consider for this project. We had around 61,000 of them. And so this data set was a pretty good data set to actually work on this project. So we also had different patient phenotypes, and this kind of helps us to kind of develop a robust model. Why even do an agentic AI model? Like, why don't we use the regular machine learning models for personalized mechanical ventilation? One of the big issues we have in the clinical AI world is that it's a black box. We don't have explainability, and using a multi-agentic architecture actually helps us convert this black box to a white box. And you'll see as all our teammates go over each of their agents and talk about how these agents improve the trustworthiness of the models as well as the outcomes. And also by using one single model to look at like the intubation, the extubation, it is not efficient. And so we need to have multiple independent agents or models which do the work and have feedback loops so that they can efficiently communicate with the other models, and so that we can have more like a trustworthy mechanical ventilation assistant. Also, another big critical gap right now in the conventional approaches are the fact that there are no safety rules which are defined explicitly. They are done through the study design, but that is the beauty of using agentic AI, and we'll see that in the presentation today. So the architecture was that we had like 5 agents and we had one orchestrator. So I'll just briefly go go over the agents, and then each of our team members are going to talk about their agent in detail. So we had like the layer one was agent A and B, which actually it looked at like, okay, what kind of cohort would this patient belong to, and from a trajectory perspective, where are they? Where is this patient at? And then the orchestrator will actually guide all the agents. It reads the phenotype. It figures out when is the right movement to intubate or extubate. Then it has all the safety features that I've been talking about. Then we have the specialist agents. So we have 3 specialist agents. We call it the sentry, precision vent, and the advisor for extubation. And in the next slides, we'll go in detail for discussing what those agents are. So I did talk about the Amsterdam DB earlier, so we can skip this. So I think Ping can take over now and talk more about, Deekshita is going to talk more about the phenotype profiler.
Hi, everyone. I'm Sai, and for a brief introduction, I'm an AI engineer currently doing my master's at Carnegie Mellon. To start with layer one, it gives you context awareness. So before any specialist agent can make a decision, the system needs to understand 2 prior questions. One is who is the patient, and the second is where are they in their illness. So these 2 questions are layer one, and these 2 agents are the profiler and the chronologist. I will be introducing the profiler. So the phenotype profiler, the profiler exists because of one fundamental clinical truth. ICU patients are not homogeneous population. The same PEEP setting that opens up recruitable lung tissue in an ARDS patient can drop the blood pressure and crash a hyperinflammatory shock patient. So the same number, completely opposite effect. So conventional ventilation protocols don't account for that. They treat everyone the same. So what does the profiler actually do? And every 6 hours, it collects 15 clinical measurements from 3 different domains. Vitals like heart rate, lab values, white cell count, and ventilator settings. It aggregates those across a rolling 6-hour window to smooth out noise and then applies a plausibility filter. So they get flagged as likely sensor artifacts and excluded before they can bias the model. Then it runs an unsupervised GMM across all 15 of those features simultaneously. And the keyword here is unsupervised, because nobody told the model what the patient types should be. It found the natural groupings in the data itself based purely on statistical density of physiological patterns across the tens and thousands of 6-hour windows of the Amsterdam UMCDB database. And it identified 2 distinct phenotype clusters, phenotype 0 and phenotype 1. And here is the part that makes this more than just a classification exercise. The phenotype label gets injected by the orchestrator into every specialist agent's reward function, and it literally changes how the entire downstream system behaves for that patient. So here are the graphs. This is the GMM's cluster assignments visualized via PCA, and the 15 dimensions compressed into 2 components, PC1 at 18% variance and PC2 at 10 to 12%. And each dot is a single 6-hour observation window across the full Amsterdam UMCDB cohort. So 2 things are worth noting here. One is the separation is stable and consistent across all the 12 time windows, which validates that these are real physiological clusters, not fitting artifacts. And the second one is to look at the 30 to 36-hour panel. That's where the blue and the red populations become more balanced. So it's the point of maximum phenotype divergence in the cohort, which is also exactly when conditioning the downstream policies on phenotype has the highest leverage. So the model reruns every 6 hours precisely because phenotype isn't static, and a patient can transition clusters as their physiology evolves. And when that happens, the orchestrator automatically reconditions all the specialist reward functions for the new state.
Hello, this is Arif Çanakoğlu. I will present the agent B. Indeed, one of our colleagues mostly work on this agent, Tian. And the chronologist had to understand the status of the patient. We want to call this system as a clinical GPS for the ICU, what is going on and where we are going for the patient. So it is not a static protocol, it's a hybrid protocol. It's hard-coded, which was defined in the promising paper. As you can see, it was defined with the PEEP and the FiO2. And we run a hidden Markov model to learn how the transition should go from one state to the other. So instead of forcing every patient in this same rigid pathway, the system learns how the patient actually move between the states. We have 4 states: acute, recovery, weaning, and liberation. Our goal is getting into liberation as the patient detached from the mechanical ventilator. So chronologist continuously every hour asks which phase is the patient currently in, and are they stable enough to move to the other state. Moving one state to the other is a confidence. There's a confidence-based trigger. A phase transition should only occur if the confidence is higher than 0.8 and sustained for at least 3 hours. This is critical because the ICU data and the status of the patient can change rapidly. It can temporarily improve or deteriorate. If you react every fluctuations, you cannot get the stable treatment, stable care in the ICU. So what the system does, it is calculating the status of the patient, which could be back and forward, but it should be the confidence should be good enough to higher than 0.8 and 3 hours rules should apply to go to worse state or better state. And we like the GPS metaphor, and I would like to present it in a way. Acute is the very heavy traffic. The patient is a problematic state, and the recovery is like clearing the roads, and weaning is the approaching the destination, and the liberation is our arrival. We don't fluctuate the state very quickly because we want to keep the patient information state stable. So tracking the patient continuously and giving this information to our orchestrator, and structuring time into the meaningful clinical phases. So thanks to this definition, the transition happens at the right moment, not too early, not too late. So we can continue to the agent, specific agent for the treatment. Next speaker, I think Chao-Ping, right?
Just briefly answer previous question. The question is, what if the patients are transitioned from one phase to another and back and forth, which is actually what happened in the clinically a lot of time. And that's exactly the reason why we choose the hidden Markov chain model. So even though they're jumping back and forth, we want to know that when they are going to be in the next status. So they will only be eligible to screening for the extubation when they are in the stable phase, liberation phase, which one of presenter will talk about later in the orchestrator part. And in the agent one part that we are talking about intubation gatekeeper, the main reason why we are talking about this because that clinically a lot of time our conundrum is that when we're looking at the patient right now, we try to decide when will be the best time to intubate the patient. Whether we should intubate the patient right now because they're struggling, or we should try some bypass, we should try some high flow. and then wait to see how the patient doing in next 1 hour or two. Because we all know that intubation itself, although it's a treatment, but at the same time, there's a lot of potential risk coming surrounding that. So by doing this agent, one of the things we try to do is to how can we facilitating the decision to make that decision. So we try to choose a causal inferential model to the T-learning trial, emulating to the target trial emulation. We try to simulation the patient intubation right now versus wait for 1 hour. And we're calculating the risk between waiting and intubate right now to calculating absolute risk difference. Then we will know that, for example, if we for patient X in this trajectory, if we're thinking about waiting for 1 more hour is going to increase the risk by 10%, then we know that there's a chance to harm the patient by waiting. In that case, we will flag the model to explain to the physician to say that if you wait for a certain time, the chance for that to happen is between the confidence range. So we will provide the confidence interval at the same time providing the potential absolute risk difference. Next slide, please. So the main result, as you can see over here, I think the main telling point is on the bottom one, the one with subgroup mean harm weighting by SF ratio strata. So you can see on the x-axis, you can see that on the right-hand side is more harm introduced with the median absolute risk reduction on the right-hand side, meaning the longer you wait, the more likely the patients have increased mortality. On the left-hand side, you have less mortality. On the y-axis, you have SF ratio from more than 250 is 0 because we specifically coded we don't want to include anyone more than 250. And 200 to 250, which is our mild ARDS range, you can see that sometimes you can actually wait for 1 more hours and before introducing any harm. And in the most severe one, SF ratio less than 150, you will see that a lot of time that by waiting for 1 more hour, you can actually potentially introduce harm for the patient. So clinically also makes sense in those severe patients. Sometimes we might want to intubate them earlier to prevent delay intubation. Next slide. Then we will give the time to Aryan.
Hey there, my name's Aryan Bhattacharya. I'm a current senior in high school, and I'll be heading to University of Texas at Austin next year to study biomedical engineering. And I worked on the precision vet. Overall here, this handles one of the hardest real-time decision-making in ventilation. How much PEEP do we give, and how do we adjust it? Well, what is PEEP? PEEP is positive end expiratory pressure, or the amount of pressure that we keep in the lungs between breaths. If we have too little, then the alveoli in the lungs collapse. But if we have too much, then we crush the cardiac system's output. It's a constant act of balancing things together, and it changes every few hours as our patient's condition evolves. The primary objective here is to minimize the amount of stress that our lungs go through. Specifically, we're targeting a driving pressure that's below 15 cm H2O. Driving pressure, which is plateau pressure, or the amount of pressure in the lungs when you hold your breath, minus PEEP, or the amount of pressure that you have after you release and exhale. That's one of the strongest predictors of ARDS mortality that we found in current literature. ARDS is acute respiratory distress syndrome, and we want to minimize that number. This agent is actively trying to bring that down. But we don't just optimize for lung mechanics and isolation. There's a hard guardrail that's baked into the reward function. If the agent's PEEP recommendation drives the MAP, or mean arterial pressure, below 65 mmHg, it takes a heavy negative reward. This makes sure that, in theory, some things might work, but this way our results from the model would be actually implemented in real life. The action space that we have is 17 different discrete PEEP adjustments, which range from -3 to +3 cmH2O in increments. This way, we don't have anything that jumps too widely, and instead it nudges between states. The state that the agent observes each step is FiO2, current MEEP, PEEP, and MAP. It's simple, and it makes sure that all of the results would be more interpretable for anyone who wants to see more. Here we can see some diagrams. For the first one, on the top left, we can see that both the AI and the clinical Q value clusters near 0 to -10 with long tails towards -70. So we see that the AI's distribution sits slightly to the right of the clinicians, which means that the AI expects marginally better outcomes at most decision points. Both are still negative because we still penalize bad outcomes, but we still have performance which outperforms clinicians. Then we can see the policy agreement. Turns out that the artificial intelligence model that I created agrees with the clinician about 72.4% of the time. The remaining is disagreements, and this is cases where the AI would do something different than what the clinician actually did. This is the overall agreement, and it's consistent with the about 75% critical severity. So next we see on the bottom left, the AI predicted improvement, which is the AI versus the clinician's Q scores. The vast majority of the decisions have a gain roughly around 0, but there's a right tail. That's the cases where the AI predicts meaningfully better outcomes than the clinician. And there's almost no cases where the AI predicts where it could do worse, whereas there's nothing significant left of 0. At the end, we see that the AI policy outperforms clinicians in predicted expected return, and the bar chart visually confirms that the AI's policy bar is actually longer and a lot better than the clinicians. Next slide, please. But beneath the hood, there's actually a bit more that goes on. Here, we use a conservative Q-learning or a CQL model. Standard reinforcement learning in healthcare has a really bad dangerous mode. This is where the agent explores actions that it never saw in the training data, and this means that in an ICU, the results could be terrible. Say, for example, someone enters the ICU and they have this much of a range, but the reinforcement learning model starts experimenting beyond that range, and it starts making decisions that would be unhealthy and things that just aren't actually true. By using a CQL model, we penalize out of distribution Q values, which means that the agent stays close to the behaviors that were actually observed in the database. This is that difference between a model that's theoretically the best versus one that clinicians could actually trust. The reward function that we have has 3 components that work together. First is the lung protection term that rewards lower driving pressure, a hemodynamic safety term that penalizes MAP when it drops below 65, because that's not good, and a phenotype weighted term that's injected by the profiler upstairs. That last piece is what makes this personalized. It's a supportive ARDS phenotype that gets different peep nudges rather than one that just changes things dramatically, even at the same FiO2. So the precision vent is always running in the background during the ventilation phase, but it only gets called by the orchestrator. Next slide, please. And the last thing that we see here is this last graph. In this graph, we can see that in this graph, we see the amount of times that the artificial intelligence actually agrees with the clinicians on the left. We can see that most of the time it's roughly 75 to 80%. But when we see on the right-hand graph, we see the Q gain by the severity. So in this graph, we can see that in most of these cases, the model actually believes that it would outperform the clinicians in each one of these scenarios. And in the critical stages, it would make the most benefits. Thank you.
One of our team members, Ajmal, developed the extubation advisor, which is the Agent 3. But as he is unable to attend, I'll just go over briefly what the Agent 3 does. So we saw the reinforcement learning outputs, and these reinforcement learning outputs are again used to predict the extubation, and also it predicts reintubation within 48 hours using a 24-hour rolling window. One of the important additions of this model was the identification of these golden 7 features. Normally, when we look at the conventional machine learning models, they use many features, like 15 to 20 features, and we've always seen that a parsimonious model works better. So we kind of analyzed many of the features, and we realized that these 7 features, basically driving pressure, peak pressure, respiratory rate, SpO2, FiO2, PEEP, and pressure support, these were doing the heavy lifting here. And so that's something that we used in this agent. We used a soft voting ensemble. So we did a lot of trial and error. We worked on different models, and we saw that using this kind of architecture with extra trees was very important to actually look at class imbalance issues. And so the output from this extubation advisor, we are able to see that we can look at the failure and success rate here. And this kind of leads to the orchestrator, which I'm going to talk about. The orchestrator is the supervisor of the model. it has two layers. The first layer is like a phenotyping layer where it tells us like who's this patient or what's their trajectory like. But then it's again guided by the three other agents. One is the gatekeeper. As we looked at like a causal inference framework. Then the other one was the reinforcement learning framework, and then the other one was the ensemble classification model. All these different models are working independently, and they come up with what the output is, but we don't directly use the output. The orchestrator is again guided by these hard overrides and soft coordination type of rules which are here. And the hard overrides are the one which gives us the safety constraints for this model. So this is something which actually helps this agentic AI framework to be a very good clinician assistant. This is missing in the conventional methodologies. I did see a question from Dr. Mathur, like what kind of tools that we use, what kind of software development tools did we use to build these agents. So this agents, for these agents, we do not use an agentic AI framework like LangGraph or the agentic development toolkit, but the orchestrator actually acts exactly very similar to the LangGraph. There are different states, and each state actually are fed inputs from the multiple agents, and we have it's again rule based, so that there are like these limits which are placed on the outputs, as well as there are again transition. The soft coordination actually helps us to understand where, again, as Dr. Mathur had this other question where like, okay, what happens when there are these phase transitions? The orchestrator has logic in there to handle the phase transitions very smoothly. And we can see here, these are some examples for the patients in Amsterdam DB dataset. So I just show here only the orchestrator and two of the agents here. So we're looking at the PEEP and we're looking at the confidence. And the orchestrator behaves like a very efficient state machine. This actually, by being able to visualize the different states that the orchestrator moves into, this is the explainability part that I had mentioned at the start of the presentation. Also, the hard guardrails and having the safety profile as something very, very important here. It can override many of the outputs if for any reason one of the outputs from any of the agents are not in the specified limits. Our study had limitations because this was a datathon. We worked, it's a single site ICU, and we do plan to expand this and use it for different data sets, do external validation on this. Also, we did like off policy evaluation. We did not do any prospective comparison yet. So our goals are do external validation, do a kind of like a silent pilot using this. And thank you very much. Please let us know if you have any questions.
Yeah, that was amazing. And how long was the datathon for? Correct me if I'm wrong. It's like just a couple of months, right? So this was
no, it's just 1 month.
Yeah, 1 month. So to do all this work in 1 month is just unbelievable. So congratulations to the team and congratulations for winning the award too. And extremely complex concepts, like both the clinical concepts are extremely complex, and we see the agent frameworks which are evolving, which are extremely complex. So to bring these two complex things together in a diverse team environment is amazing. So kudos to you guys. One thing I wanted to understand from this is because many people will be looking to build such solutions. How did you work together in such a short time frame? And I think that was one of my questions to Anirban, but to the rest of the team too. mean, we see like Aryan, who's a high school student, all the way to Sai and Preethi and Chao-Ping, and of course Arif, who's very, very experienced. How did you make this a coordinated effort with the same level of understanding? Because more than building an agent, I think it's the team dynamics that we need to understand a little bit better, especially in the short time frame. What would your advice be to others who are trying to do the same?
Yeah, I can take a stab at it and then others can answer. So what we did was we tried to make it a level playing field for everyone, right? So uh, you know, create resources like Notebook LM or Gemini where you dump the current literature. So for I'm a doctor by training, so I can understand the medical side. Preethi or Arif are full-fledged computer engineers by training, so they can dump the other side, right? And then what these tools do is allow you to have a conversation with them and personalize the amount of teaching and learning that you need to develop those concepts so that we all kind of arrive at somewhat of a common minimum, and from there everybody takes leadership ownership of certain aspects of this. The other key aspect was communicating frequently and daily. So we tried to hold a meeting every day, knowing that it's going to be hard, but something we tried to adhere to, even if it's for 5 minutes. I think those things worked well. What do you guys think?
Also, I want to add that the advantage of working on agentic AI models is that every agent can be developed as a separate module. And so you can do like unit testing and get that working really well. And then, for example, I was working on the orchestrator at the end. So I was looking at the outputs of all the agents and the profiler and the chronologist and trying to see, does that make sense? But everyone could go off and work on their own. So which was not possible when you work like on a very like single machine learning model. Like you need to have like one single code base.
For me,
Yeah,
one of the best
go
parts
ahead.
of working. Oh, sorry.
Go ahead, Aryan, please.
For me, one of the best parts of working with the team was that though I'm still like one of the younger people on the team, I felt comfortable asking whatever questions I wanted to, and I also had guidance. So being able to reach out frequently and like use my past experiences and continuously be ready to learn was the best part that I felt made my contributions to this team productive.
Yeah, what I was telling is similar to the others. So everyday meeting was really helpful because it looks like we are doing every week. Every day was a 1 week. So we were updating each other. Everybody tells what he did, what he wants to do the day after, as well as we were giving recommendation to the others what we want to do, how to reach our position. We have every level of the person, as Aryan said. He's the youngest one, high school student, and we have also the work in different levels. So we are trying to get each other's opinion, and we have a very high work power. Thanks to each agent has different structure. Thanks to that, we don't need to wait the others. So when the data is there, we were running the models and getting into the system, and at the end, from the data to the orchestrator, every agent works and learn the models by different persons. So these two things works very well this year. Also this year, I can say.
That's great. So the next question from Teams is to tools. So I see like there are a lot of these agent development kits out there. There is one from OpenAI, there is one from Google, and there's so many of those over there. So what are your thoughts on trying to build these agents versus using some of these agent development kits?
So yeah, so I think we can kind of divide them into two parts. Like one is no code agents, where someone, like for example, a clinician who does not have any programming experience, they can still go and create these agents and just use English. We kind of use the opposite approach, where ours is like full code, like we wrote the code ourselves. But again, I think by coding yourself, at least you know for a fact that you have a very robust model, and it can be expanded to use other data sets. I think somewhere in the middle, maybe if we have to redo this project all over again, I may use LangGraph, and do the state machine using that. But right now, I kind of coded it, and then you can always use Gemini or ChatGPT to kind of discuss what's the better model which can work with this kind of thing. But it's always good to have like some AI data scientists to review the code, even if it's like completely vibe coded. At least I like maybe other team members can talk also about their experiences.
Yeah, one of the things that I found is exploring some of these development kits, that they all have their pros and cons. Some of them have limitations onto, the different tools that you can use, or even the different LLMs that you can call. So we just have to recognize that all of them will have, some or the other challenges, because they're trying to direct you to work through their proprietary resources or what they have collaborations with. So that is something that I found while trying to build this. The other thing is that many times there are upgrades made to various libraries or various tools. So if you have built it, just be cautious. It's possible that some of those might get upgraded, and all of a sudden you realize that your agent is, or some other part of the multi-agent framework is not working. So that's where there are some pros and cons to how you build it, especially in a clinical deployment space. That becomes very, very critical from my point of view and my experience.
I think I'd like to add on to that, and I agree with you in this sense. We had like, because we had 1 month, there was a lot of back and forth in terms of like, okay, is this clinically relevant, and the clinicians would give their input on that, and then we'd go back and then code and change, and there was a lot of flexibility in those terms, and maybe with the framework we wouldn't have that kind of transparency. But again, like you said, there are a lot of pros and cons associated with it, and like Preethi said, maybe if we go back and when we think about it now, it seems like it would have been easier to use more of a rigid like framework or like a kit. But however it turned out, I believe that it gave us a lot of experience in terms of especially to beginners like me or Aryan, to like hard code it and to learn more in each of the agents and exactly how the orchestrator is coming together.
That's great. Okay, so from team to tools to impact. So how do you make it impact? For the implementation is the hardest task, right? So how do we go from here to implementing it?
So, I think we are currently, debugging. Obviously, it was all done at a lightning speed, and we used every moment that was available to us in that 1 month. But now is the time to go back, make sure that, we are happy with it, the areas that we want to improve. So once we are done with that, I think obviously there are two forks, right? One is you look for a clinical publication, or publication in a manuscript, maybe more than one publication. Uh, and the other piece is taking this model down to uh, a prospective data set, or even, a different data set, and trying to see how this, whole uh, system performs. So we are, you know, probably that is after we are ready with what we are doing. Uh, so that's where we are at. That's what we are thinking. But yeah, happy to hear, suggestions. And obviously, our team members are very knowledgeable. They've worked in this field for a long time.
Yeah, I think one of the challenges that we have to think about, our team BrainX AI Research has been researching this for some time too, uh, is the challenge of evaluation. So with LLMs or the foundation models, we built certain evaluation tools. We start with human evaluation tools, which is humanely, and you can see it on brainxai.com. It's freely available. Anybody can use it. But then we had to scale it. So we developed a LLM as a judge model where you can use LLMs as a judge to look at LLMs outputs. But now with these agentic frameworks, it becomes even more complex. And that's where when we go into the evaluation part of it, prospective trials point of view, I think it becomes even more complex. And I think there are some current concepts that are being developed that I've seen, whether it's evaluating the output, net output, or looking at the traces throughout the agentic work. But I think a lot more needs to be done to understand how to evaluate, especially if you're going to implement these. And just like LLM ops or ML ops, I think there might be like a whole field of agentic ops that might be opening up to look at continuous evaluation. Because if you're going to deploy this in a clinical space, the evaluation has to be constant, and there has to be some way to pick up any errors or any deviances that we might see. So, any thoughts on the evaluation part of it? We are very excited. A lot of our team members are researching this space very actively, and hopefully, we'll come up with some tools soon to do that too. But any thoughts from you on evaluation part?
Preethi or Ari, you guys want to take this one?
Yeah, so in clinical deployment, even at Mayo, this is one of the biggest challenges. Like, let's say you have 6,000 patients, we can't recruit clinicians to go and look at all these 6,000 patients. One of the ways we're trying to overcome this at Mayo is that we are able to have two kind of evaluations. One is very similar to what you've been talking about, Dr. Mathur, like the humanely, or like trying to do more like a qualitative evaluation, like how well is this LLM response? How does that look? And then the other one is the quantitative. And luckily for our project, for this personalized mechanical ventilation, we do for doing we can validate using retrospective data, because we do have the answers. We do know what the clinician outcome was, and that is somewhere like where the agentic AI is very important, is that we can actually make it really smart. We do have reinforcement learning, but we can also add more other agents to make it smarter, like to observe the outputs and make sure that the agents themselves are doing what they're supposed to do, which the present LLM models as well as the earlier machine learning models, they don't have right now. And this is very important for clinical deployment. But at the end of the day, at least for 10% of the patients, there needs to be some kind of clinician who has to at least go and check everything is looking good. At least that's like the golden rule right now for clinical deployment. We don't have enough confidence to just go and deploy an agent and say it's going to be great. Also, the other thing which can really help is to add a chat option. That, let's say, our personalized ventilation, we know that this is what the orchestrator is saying this, but then by adding an LLM component to this project, the clinician can chat and figure out, give more details, and that gives the explainability and trustworthiness. But at the end of the day, the clinician is the controller. The clinician decides what needs to be done. This is just an assistant. We'll just give an advice.
Awesome. Arif, any thoughts from you?
Yeah, I do agree with Preethi. Indeed, these agents will not get into the system directly and give the last decision. It will be advisor or consultant to the medical doctor. So, and the evaluation is the hardest part. We are always talking about this in the 1 month of the data tone, as well as we want to continue on this project. Our main problem is how to evaluate our agents. Each agent can be evaluated easily because they are models, but especially the orchestrator is the most difficult one. How to get it gives the correct decision or not, how get the credibility of that, how the confidence should be given to the last user, the medical doctor as well. So this is what we are thinking as well. Unfortunately, we couldn't yet find the problem, but we are working on that. Piyush, you are muted.
Yeah, thanks for reminding that. With that, we'll come to an end of this session. Very exciting concepts, very complex concepts coming together through this. But hopefully, through your shared experiences, many of those can learn and can work on their own agents. And we actually, when we wrote the year in review for 2025, that is something that we had predicted, that this is a year where we'll likely see a lot more research work on AI agents and publications related to the same. So probably when we do the 2026 year in review, we'll start seeing a lot more publications related to this. But it's very important to share this information so that we can all learn from each other and work together to build solutions, the agentic AI solutions that can truly help us. So thank you, everyone, for your awesome presentation. Thank you to the participants who joined us. Hopefully, it was a great learning session for you. Continue to follow us on BrainX Community through all the different resources that are there on the slide. Until next time, follow us on BrainX Community. Take care.